So in this video, we are going to learn about discrete random variables. We're also going to find its standard deviation, also known as the expected value, and also the standard deviation away from that average. Now, you might, from the previous videos that I've done, remember about the word discrete. Discrete means easy to count. So a discrete variable is easy to count with whole numbers, 0 through as high as you can go. So we are going to look at a discrete probability distribution. Now, they have two characteristics. Each probability in a probability distribution is between 0 and 1, inclusively, which means that you could have a 0 or you could have a 1. Another way to look at this mathematically is to say 0 is less than or equal to the probability, which is less than or equal to 1. Or the probability is between 0 and 1, including 0 and 1. Now, another characteristic of a probability distribution is that the sum of all probabilities is 1. So if you take every single thing that is possible and add them up, it equals 100%. Or the sum of the probabilities is equal to 1. So in our first example, we're going to take a look at a game called the grab bag. Now let's say that you were lucky enough to pull from the grab bag, and the grab bag has $1 bills, $5 bills, $10 bills, and some $20 bills. It would make sense in the grab bag that you would actually have more of the lower denominations than the higher ones. So in this case, our X is the event of pulling one of these bills. So you could either pull the $1 bill. Oops, I should move that over one space here. Pardon me. So you could pull the $1 bill. You could pull the $5 bill. You could pull the $10 bill. Or you could pull the $20 bill. Now, if you take a look at the wording here, it gives you some probabilities, because it tells you there are 10 $1 bills. So there are, I'm going to do some side work here. So the count, this is 10 $1 bills, 5 $5 bills, and 3 $10 bills, and 2 $20 bills. So if I add these together, these frequencies, I then get my total here. 10 plus 5 is 15, plus 3 is 18, plus 2 is 20, which happens to be my total n. So to figure out my probability, picking out a $1 bill would be 10 out of 20, or roughly half, or exactly half, excuse me. And then 5 out of 20 to get a $5 bill, 3 out of 20 to get a $10 bill, and then only 2 out of 20, or a 10% chance, to get a $20 bill. Now, the formula for finding the expected value is the average. So the average of pulling a money out of this grab bag is going to be the expected value. So what do you expect you would get from every single pull? Now what you're going to find is that this number isn't exactly one of these dollar denominations. The answer is not probably going to be $1, $5, $10, or $20, but it's basically saying how much are you expected to get upon each grab. And the formula is this. It's the sum of all of the possibilities multiplied by their probabilities. This gives you the average or the expected value. So if we move this down a little bit, let's show some work. So the sum of x times p of x, sometimes with an extra set of parentheses, just to show you that we're adding the x times the p of x and not just adding the x's here. We're going to take our first x of p of x and say, okay, I can win $1 and I have a 50% chance of getting that dollar. Plus, I can win $5. And then I'm going to have 5 out of 20 chances to get that, which is 25%. Plus, I can win $10, but I only have a 15% chance of winning that. Plus, I can win $20, but I only have a 10% chance of winning that. Since I'm going to type this into the calculator, there's no reason to reduce these fractions. Now, when you type this into the calculator, make sure that you use the parentheses keys. That's above the 8 and the 9 key on most graphing calculators. And then put the division sign as your fraction bar. If you type this in correctly, you get an answer of 5.25, which is $5.25. This is your expected value, $5.25. Now, it is impossible if you're playing this game to pull out $5.25 since the denominations of winning is $1, $5, $10, $20. But what's important to know is that the person who's supplying the money for the grab bag game is roughly losing about $5.25 on average per draw. Even though no one's taking a quarter out of the bag, this is the average built on this weight based on the probabilities that each one can happen. So the therefore of this is that $5.25, pardon me, my 5 didn't look so good there, $5.25 is your expected pull per grab. So the expected value is a little bit more than $5. Now what you can do if you're actually creating this game is you have to think to yourself, how much would I have to take in before I let someone play this game? So if you wanted to make the grab bag game a casino-like game, you would try to basically take more than $5.25 per grab, because in the long run, according to the law of large numbers, you will actually come out ahead. Because the more trials you do, the closer you'll get to this theoretical average. So to continue on, we are going to take a look at this grab bag problem, and we're going to apply the standard deviation part of this formula. Now, the reason why we are going to look at the standard deviation is because we need to know how good our average is. Because as it says here, the average is only as good as its standard deviation. One of the things that you should probably realize, since we've been through some of our earlier statistics, is that if someone gives you an average without a standard deviation, that's probably not really good statistics. Because what we have to figure out is what's actually normal. So the first standard deviation tells us the boundaries of normal. And we're going to put normal in quotations, but to kind of show you what I'm talking about here, is that the expected value on a normal curve of this game is $5.25. So what's considered normal? Well, one standard deviation away would give you what's considered normal. So if you knew that this game paid off roughly $5.25 on average, give or take the standard deviation, this might help you, first of all, not only make a good idea of what to charge for this game, but it also, as someone who's playing the game, it's a good idea to know how far the variation is on this. So let's actually use this chart to help us out. So to help us out, we're going to take the chart that we had going horizontally, and we're going to change it into a vertical chart with $1, $5, $10, and $20 going vertically, and the corresponding probabilities. And this was taken from the previous side. Now we're going to multiply our x times p of x, So this 1 times the 0.5 is going to be 0.5. The 5 times 0.25 is 1.25. The 10 times the 0.15 is 1.5. And the 20 times the 0.1 is going to be 2. We're going to need this x times p of x to get a total. If I add these together, 0.5 plus 1.5 is 2, plus another 2 is 4, plus 1.25, this gives me 5.25, which we found out on the previous page. Now, this average is incredibly important because remember from our previous lecture that mu means average, and it gets the Greek letter because this is the theoretical average. We are going to take our x, which is our event, subtract our average, and then square it. And then multiply that by the p of x. So it's a lot going on just for this column here. So let's take it slow. The x for this column is $1, minus our average, which is $5.25. Type this exactly as you see it into the calculator. And then we're going to multiply this by the probability of x. So you can go 10 divided by 20. If you do this correctly, we're going to get 9.03. Then we're going to go 5 minus 5.25. Again, taking our event, subtract it from our average, and then multiply by its probability, 5 divided by 20. And that would give us 0.02. It's not a big number because the difference between 5 and 5.25 is very small. Okay, for our next problem, we're going to go 10 minus 5.25, square that, and then we're going to multiply this by 3/20. This gives us 3.38. And finally, this one, it's pretty big because 20 minus 5.25 is a pretty big difference. We square that but multiply by a very small number. This will give us 21.76. So, we're going to add all these up, and this will give us lowercase sigma squared, which is 34.19. Lowercase sigma squared is the variance. This tells us how spread out our numbers could be. We don't really talk much about variance, but we spend a lot more time talking about what we do next, which is taking our square root of both of these numbers, and this gives me lowercase sigma, which is the square root of 34.19, which is 5.85, and this is going to be our standard deviation. So completing this column and then taking the square root of the sum will get us our standard deviation for this problem. This makes me want to go back up to that bell curve that we had near the top of the page and talk about that game. Because the game has an average payout of $5.25, give or take $5.85. So if I add $5.85 to the $5.25, I get $11.10. And if I subtract the $5.85 from, from the $5.25, I get negative 60 cents. So this means that I'm going to get, on average, $5.25, give or take $5.85. But that means I'm going to be between 60 cents and $11.10. Now, what's important about that, and what I just did here, is this means that I am going to be expecting to get nothing to $11 when I play this game normally. So it's not normal for me to get more than $11, so getting the $20 bill is not going to be normal. And it's definitely not going to be normal to get nothing, because you can see that I'm going to get $1 from this game. So that's the standard deviation and how it kind of plays into this problem. I'd like to do one more example from this kind of a setup here, and I want to do it with vacations. I want to do it with vacations here. So let's take a look at families who take vacations. Now, this table reveals about how many 5-day vacations a family takes each year. So what that means is that there are, if I'm going to follow this here, 6% of the families take 0 5-day vacations. 70% of the families take at least 1 5-day vacation, or several vacations that add up to 5 days. 20% take 2 5-day vacations, or have 10 days of total vacation. 3% has 3 5-day vacations, or 15. And then 1%, we're just going to take all the ones that are 4 or more and just say, okay, that's roughly 1%. So let's find the expected value, or average. So 0 times 0.06 is 0. So we're not going to get any of those. So 1 times 0.70 is 0.70. And 2 times 0.20 is 0.40. And again, I'm using some extra zeros on there to be stylistic. You can drop those off if you would like to. 3 times 0.03 is 0.09. And then 4 times 1/100th is going to be 4 hundredths. Now, if I add these up, I'm going to get an answer of 1.23, and that tells me that my expected value is 1.23, or the average family takes 1.23 family vacations. So closer to 5 than 10. So what could we do? Estimate that to be around 6 or 7 family vacations? Closer to 6? All right, so that's kind of nice. So we now know that the average is 1.23. Oops, I wrote a 5 there. Let me change that. But what's the standard deviation? So what is my give or take on this situation? Well, let's go figure it out. Let's take my event, subtract my average, square that, and then multiply it by the probability, which is 0.06. If I do that correctly, I get 0.091, or 91 thousandths. Okay, for the next one, 1 minus 1.23, square it, multiply by the chance of this happening, 0.70, we get 0.037. And we're going to be adding all these for the total column here, but let's keep going. 2 minus 1.23 squared times 0.20. This gives me 0.119, or 119 thousandths. 3 minus 1.23, quantity squared, times 0.03. This gives me 0.094. Finally, 4 minus 1.23, quantity squared, times 0.01. Don't know why I just dropped parentheses right there. Just trying to keep everything consistent. There we go. That is going to give me 0.077, or 77 thousandths. Now, if you add all these up, you get an answer for sigma squared, lowercase sigma squared, 0.418, and that's my variation. And here's what's great, because what we can do next is we can take the square root of this. So take the square root of the sigma squared, which gives me just sigma. And then take the square root of the 0.418, which gives me 0.65. And this is my standard deviation. So we got our 1.23, give or take 0.65. So if I add my 0.65 to this, I get 1.88 vacations. So closer now to 10 days on the normal side, on the high side of normal. And then if we go down 0.65, we get to about 0.58, which is a little bit more than half a week or half of the 5 days, so closer to 3 days vacation. So we can say, since this was 1.23 was, approximately 6 days, and this was a little bit more than half of 5, so this is 3 days. So following this pattern here, then this would be 9 days. It is normal for people to take a 3 to 9 day vacation. It's, of course, more normal in the 6-day range, but that's actually pretty nice. Look how close that standard deviation was. That's really great. I mean, you're finding not a lot of variation here. We have some vacation time, and it would be weird if we were less than 3, or weird if it was more than 9. And that's how we do standard deviation and expected value or average of a probability distribution.